Okay, let's continue. So in the last couple of weeks, we essentially were looking at some of the non-idealities that you might encounter while designing analog circuits. So the first thing we saw was mismatch, and the effect of mismatch was twofold in our op-amps. First, we noticed that we have what is called a common mode to differential mode conversion. That is, although you have a fully differential circuit, if there is mismatch, if you provide a common mode excitation, you get a differential mode output. The second implication was that you have offset in your amplifiers. And what is one brute force way to reduce mismatch in all circuits? Increase area. That is one brute force way. But it turns out there are other circuit techniques that can be used to eliminate offset. And even for this common mode to differential mode conversion, if you have a very good common mode rejection, this gets resolved. And how can you get a good common mode rejection? Or first of all, what is giving you common mode rejection in your diff amp? Huh? And fundamentally something else is already giving you. No, let's say you take normal diff amp, okay, the tail current source, right? So if you have a good tail current source, you can actually go and tackle this. So what I'm getting at is mismatch is not something really fundamental. You can come up with circuit techniques to get around the problem. The second non-ideality we saw was thermal noise. But unlike mismatch, thermal noise is something fundamental that has been chasing you since you learned thermodynamics. So there is really not a lot you can do to avoid noise. Only thing as a designer you can do is understand what will be the noise that will be present in your system. You should be able to calculate what is the noise part spectral density and so on. And once you calculate, you can design your circuit so that the noise specification is met. That's the only thing you can do. Okay. Cool. So now we'll look at the third non-ideality, the last non-ideality in our course, and that is essentially non-linearity. And I'm sure non-linearity is not something new to you, because if you take our old friend transistor, which is MOSFET in this case, you know that in a MOSFET the drain current is a non-linear function of the gate to source and drain to source voltage. So essentially if you sketch the drain current versus VGS, it has a non-linear characteristic like this. And if you actually think about it, non-linearity is not something you do not want in your circuit, right? Because if you recap your first analog circuits course, to get power amplification, what is something that is essential in all your circuits? Non-linearity is something essential to get power amplification. So non-linearity is not something you do not want, but too much of non-linearity is something you don't want to have. Right? So as I say, non-linearity is like food, right? I mean, food is something that without which you can't live with, but too much of food is also something you can't eat. Right? Same thing here also. But although this characteristic is non-linear, we have been doing the same thing for last few courses. If the input amplitude is sort of restricted to a small range, in this small range the characteristic can be approximated as a linear thingy. So if the input is essentially varying small like this, then you can approximate the drain current. We'll call this Vi. Then you can call the drain current to be a linear function of the input voltage. That's done. But of course now let us say the input spans a wider and wider range, which is something you might want to have because you want to have large signal to noise ratio, which means you want your signal amplitude to be as large as possible. So the moment the signal amplitude spans, let us say, such a wide range, then obviously this is no longer a linear characteristic. Or in other words, if you calculate the GM at this operating point, that is going to be different from the GM calculated here, here and so on. In other words, the GM is not a constant now. It itself is a function of the applied input voltage. Right? So which means I can no longer write the drain current as a constant times the input, because this GM itself is a function of the input. Make sense? So of course now you can use your favorite power series expansion. So you can expand it on polynomials of Vi. So you might get something like some GM1 times Vi GM2 times VI square. Yeah. Which one? Oh yeah, I mean what I'm saying is VB is constant. Yeah, see, it's a constant. The only variable here is VI, right? Of course, it is dependent on VB, but that's relevant. Right? So something like this. Now, of course, this drain current flows through the output resistance of this transistor to get the output voltage, and the output resistance is something that is arising because of the dependence of drain current on VDS, and even this dependence is nonlinear. So finally, you will find that my output is a nonlinear function of input, say some alpha 1 times Vi, alpha 2 times Vi square, alpha 3 times VIQ plus dot. So at least till this point, it should be very clear that if you have a single transistor like this, the behavior is going to be nonlinear. So which means any circuit that you build using transistors, they will be linear or nonlinear? Nonlinear. So let's say now you have designed an op amp with MOSFETs. So we can be guaranteed that this op amp will not be a linear op amp. In fact, the input output characteristic might have a nonlinear relation like this. Oops. Okay. So which means now let us say at the input I feed in a sinusoid at a frequency f0. Then I look at the frequency spectrum of the output. What are the sinusoidal frequencies that I'll observe in the output? I'll get f0 for sure. What else I'll get? I'll get 2f0. What else? Yeah, and you also have a zero component, DC, right? Because remember, if I have alpha square, I mean Vi square, cos square x is 1 by 2 plus cos 2x by 2, you have a DC term. So you'll have all harmonics. So which means if I sketch the frequency spectrum, it roughly will look like this. You have the fundamental at f0. So you have some DC, some second harmonic, third, fourth, and so on. Okay. Cool. So now we at least know that if we have a nonlinear system, the spectrum is going to be corrupted like this. So now let us say I have two op amps, and if I want to make a comment as to whether the op amp 1 is more linear than op amp 2 or vice versa, then I need to have some way to measure or quantify the linearity of my circuit. And it turns out depending on the context and the system that is being considered, there are multiple different metrics used for quantifying linearity. For example, if you take RF systems, you will have one set of metrics. If you take data converters like ADCs, you will have one more set of metrics. But at the heart of all linearity metrics, what will happen is this. We know that if you feed in a sinusoid at f0, you get the whole bunch of harmonics. So to quantify the amount of nonlinearity, we sort of see what is the strength of all these unwanted harmonics with respect to the required signal. That's the basic idea, and the actual definitions might vary depending on the kind of system you are dealing with. So one probably a common metric is what is called as harmonic distortion. And in particular, if I call it harmonic distortion 2, HD2, this just says what is the strength of my second harmonic relative to my fundamental. That's all. So typically this will be a very small number in practice. So if you have very small numbers, you don't deal with absolute scale. What do? You take log scale so that you can represent wide range of values. So this is represented in decibels typically. So which means if the spectrum itself is plotted in decibels, in log scale ratios becomes ratios difference. So the difference directly gives you HD2. Similarly, you can define third harmonic distortion HD3, same way. It's nothing major there, but there is something that we should have in mind while dealing with linearity matrix. So let us say I have two op amps again. So let us say the first op amp has a harmonic distortion of second harmonic distortion of say minus 60 dB. This guy has minus 66 dB. So if I give you just this piece of information that the second harmonic distortion is minus 60 and minus 66 here, which of the two op amps do you think is more linear in terms of at least second harmonic? Huh? First one or second one? Second one. But okay, hold on to that thought before jumping to that conclusion. So let's say to measure the second harmonic distortion, we know I'll have to feed in a sinusoid at f0. Look at the strength of 2f0 component. So let us say I feed in a signal which is like this, v in 0, say sine of 2 pi f0 t, and then I measure what is the second harmonic distortion. Now let us say I repeat the same experiment by applying the same sinusoid but with twice the amplitude. I can do the same thing, same experiment. So do you think the second harmonic distortion will remain the same or will it change? Same, change? Huh? Same, why same? Okay. I mean, logically tell me, if the input signal I apply has smaller and smaller amplitude, will the system behave more linearly or non-linearly? Linearly, because your small signal linear approximation is going to be valid more. So which means if I increase the amplitude, the non-linearity should be more pronounced or less pronounced? Small signals, it's more linear. If I apply large signals, will it be more non-linear, right? Yeah. So non-linearity is more pronounced. Fine. So which means SD2, do you think will it remain same? It should increase, right? And you can actually compute it. I mean, it is essentially ratio of these two, right? So if let us say the sinusoid amplitude is v in 0, the fundamental strength will be proportional to v in 0, because fundamental term is coming due to this term, right? Similarly, what do you think the second harmonic strength, what do you think it will be proportional to? V in 0 square, because second term is coming due to alpha to vi square, so v in 0 square comes. Is that okay? So which means my second harmonic distortion is actually proportional to. But typically, oh yeah, you're absolutely correct, because you're saying sine cube x has a sine x component, right? Yeah, but no, sine 3x has, yeah, sine cube x also has sine x component, I agree, but typically that's going to be much smaller. The assumption is alpha 1 is greater than alpha 2 greater than alpha 3, right? So this is going to, I mean, remember you are going to make an amplifier. So the linear gain, you want it to be small or large? So you are absolutely correct. If you compute the exact strength, it is going to be dependent on alpha 3 also, because sine cube x also has a sine x component, right? Sine cube x is sine 3x plus 3 sine x by 4. So you also have a sine x component, but that's small, so we neglect. Okay. So HD2, as you see, is proportional to v in 0. And similarly, what do you think HD3 might be proportional to? V in 0 square. So which means if I just give one piece of information that HD2 so much, that alone is not sufficient, because for all that, you know, maybe this was characterized with 100 millivolt sinusoid, this was characterized with 10 volt sinusoid. So it's not fair. So that's why when we report the distortion performance, it's all reported at the maximum amplitude you have, because that's where the absolute test comes. You can't say apply 1 microvolt sinusoid, my system is completely linear. No one cares. You check what's the performance at the maximum possible amplitude you can have. Okay. Cool. So now at least this part should be clear. Yeah, that. Okay. Any questions on this?
How do you know the maximum possible amplitude to test?
Good question. How do you know the maximum possible amplitude? You design an op amp. What do you think might be the maximum signal you can give?
Small signal assumption that we are doing.
That means you are operating trying to make it more linear. What is the maximum signal you can give? The swing, I mean, you have 0 to VDD. What is the maximum signal you can feed? Right? Or maybe slightly smaller than VDD. I mean, but yeah. Right? But that's what happens. You can't arbitrarily give 100 volts and say, if the supply is 1 volt, yeah, maximum we can go is 1 volt, not more than that. Cool. So now to give you a feel for what happens in practice due to nonlinearity, I did the following experiment. So I generated a sinusoid at 1046 hertz. Question? Don't ask. It's okay. It's okay. Don't feel sick. Yeah. 1.8 volt, right? But I thought in the you mentioned regarding the PDK. What did you guys use? Oh, same VDD. I mean, same technology, same VDD, right? I mean, okay, I thought it's clear, but yeah, if it's not clear, VDD is 1.8 for the technology. Okay. So, anyways, to give you a feel for what happens due to nonlinearity, I generated a sinusoid at this frequency, saved it into an audio file. Then I sort of passed it through a nonlinear system having a second order nonlinearity like this, and saved it into another audio file. So let me see if I can play it here and see how it sounds. I think I'll have to disconnect it, otherwise it will play from the projector. First I'll play the pure sinusoid now. You are able to hear, right? Okay, hold on. Sorry to make you go deaf, but if you are musically inclined, this should sound like a music note C in the 6th octave. But yeah, I mean, maybe the speaker is not great. So now I'll play what happens after I add the distortion. Okay, you're not able to listen clearly. Maybe the other side. Hold on. The speaker is not great, I think. Now you see the change in the performance. Again, if you actually have very good earphones and listen, even for the previous one, you would have heard very distinct this one. But yeah, I changed the nonlinearity. The first sound I played, the nonlinearity was not so much. The second time I made the nonlinearity to be 10%. So then you could actually distinctively hear. Right? And in fact, it turns out the most stringent requirements for linearity comes from audio applications. So, I mean, you know, all the audio is sort of recorded digitally. So, there the linearity requirement is about 100 dB or so. 100 dB is essentially 10 power 5, right? So, which means if your fundamental is 1 volt, all your nonlinear terms must be having 10 microvolt amplitude or smaller. So, this is one of the most stringent requirements. Okay, so now question to you. So, let us say if I sketch the pure sinusoid, which I played first, it looked like this. I mean, maybe I'll draw it like a nice sinusoid. It's not a nice sinusoid. Okay, assume that this is a nice sinusoid. Now, after I added the nonlinearity, the distorted sine wave, how do you think it might look like? Any guess? That's all true, but in time domain, if I look at it, how do you think it might look like? That's what I'm asking.
The same but small ripples.
Okay, small ripples like this, huh? Any other? Okay, second, thing is top is clipped like this. This is the typical understanding, but before again jumping to conclusions, let's look at what happens. So here I am showing the pure sinusoid, okay, 1046 hertz. Looks like a sinusoid. It is a sinusoid. Here next I will show the waveform after I added the distortion. That's how it looks like. So bottom line, it is almost always impossible to see if the waveform is distorted or not just by looking at the time domain waveform, because the usual understanding students have is if it's distorted, it sort of gets clipped like this. That is an extreme level of nonlinear distortion, but in almost all practical cases this doesn't happen. You deal with nonlinearities like what I demonstrated, and for those cases, just by looking at time domain, you can't make sense of whether it is linear or not. So if you can't detect in time domain, what do you do? Frequency spectrum. And if you do that, this is the spectrum of the pure sinusoid. As expected, I see only one tone, the rest is all noise. Here I am showing the spectrum of the distorted sine wave, and as expected, I see two tones, 1046 Hz and twice the thing, 2000 amplitude. So that's why as circuit designers, you should all be very comfortable in handling frequency spectrum, plotting FFT, DFT or whatever you do. Because most of the time measurements are done in frequency spectrum, because time domain does not yield a lot of insight most of the time. Cool. So now at least we know that is the okay. If you take spectrum, what is x and y axis? X is frequency. What is y? Same thing, right? This is the magnitude of the sinusoid. I mean, this is in decibels actually. This is minus 19 dB. It means, I mean, this is minus 20 dB roughly. Okay. So at least now you have a feel for what happens when there is nonlinearity, and you know some metrics for characterizing nonlinearity of circuits. And if you want to exactly go and sit and calculate what is the nonlinear term generated in your circuit, there are mathematical tools that help you compute. But again, you'll end up with pages and pages of long equations. And I always feel only mathematicians will derive pleasure in looking at long equations. As circuit designers, we don't want to do it. See, as a designer, if at all you do any analysis, there should be some use to it. That is, after you do the analysis, it should help you make your design better. If it is not giving you any help in designing circuits better, then there is very little sort of use to the analysis. Right? So that's why we will not look into the detailed analysis of how to deal with nonlinearity. We look at it very briefly later, but for now we'll just try to have a very qualitative understanding of the kind of nonlinearity we can have in our circuits. And we are dealing with op-amps, and as we saw, most of the op-amps designed on chip, they are fully differential. So let's see what is the kind of nonlinearity you can expect in fully differential circuits. And for that, I'll consider a simple block like this: one half circuit, another half circuit, and something that is common. Very crude representation of a fully differential circuit. Let us say here I apply plus Vi, here I apply the minus input. Reduce this maybe, and let's say I call this VO plus and VO minus. And as usual, the half circuits are nonlinear. So which means if I try to find the output in the positive side, it's going to be alpha 1 times Vi, alpha 2 times Vi square, alpha 3 times Vi cube, alpha 4 times Vi power 4, and so on. Similarly, if I find the output on the negative side, how do you think that will look like? I mean, if I know this, how can I get VO minus? What do? I'll replace Vi with minus Vi, that's all. So then I'll get minus alpha 1 Vi plus alpha 2 Vi square minus alpha 3 Vi cube plus alpha 4 Vi power 4, and so on. Now please remember, in fully differential systems, we are not interested in the individual outputs VO plus, VO minus. What is the actual signal of interest? Difference between the two. So if I take the difference between the two, what happens? All the even order terms cancel. So this even terms getting cancelled is good or bad? Something is getting cancelled. Why good? Yeah, at least now you see that earlier you had all orders of nonlinearity. Now at least the even powers completely get cancelled. Right? So that is an important feature of fully differential circuits. So you will have no even order nonlinearities. and you'll have only odd order distortion. Okay. Is that fine? So which means if I feed in a sinusoid at a frequency f0 in a fully differential system, the output will contain what all sinusoidal frequencies. Yeah, I'll have the fundamental and 3f0, 5f0 and so on. Again, you will have only odd order non-linearities, so only odd harmonics will be present in the output. Okay. So, okay, now tell me, do you think in practice the even terms exactly get cancelled like this, or there is something else that might limit the extent to which the terms get cancelled? Mismatch? Because here I sort of assume that the two halves are completely identical, but as you already know, there is going to be mismatch. So in practice, they don't exactly get cancelled. So they will get cancelled, but you will still have some residual second harmonic, fourth harmonics, and so on. But typically, they'll be very small, but it is not like it is completely eliminated. So I'll say that this is assuming there is no mismatch. If there is mismatch, you will have small even order non-linearities, but not very significant, hopefully. Okay, so at least now we know one piece of information, that if I implement my op-amp as fully differential op-amp, I will not have even order distortion. So let's try to get some more understanding of the kind of non-linearity we might have. And for that, let's look at the basic building block, which is the diff pair. Okay. Okay. Yes. So I'll just take this differential pair biased with an ideal tail current source for starters. Let's say the total voltage I feed in at the gate is V1. Okay, this is not small signal, this is the complete large signal V1. Let's say this is V2, and I'm interested in the differential current I1 minus I2. Now at this point it should be clear the differential current will be non-linearly related to the differential input, and the goal is to try to find the nonlinear function. Again, it's not that difficult. You can assume that you have a square law characteristic for MOSFET, and then you can start. If I call this Vx, what is I1? Assuming square law, what can you say about I1? Yeah, I mean some mu and Cox W by, let me call that beta, times V1 minus Vx minus a threshold square. Again, remember, in practice this is not usually power 2, it might be some power m where m can be less than 2, but for simplicity let's assume to be 2. Okay, similarly, what is I2? Same thing, but I have V2 minus Vx minus Vth square. And what is I1 plus I2? I0. So, I mean, now we can actually use these two, take the difference between I1 and I2 and sort of do some algebra and get this nonlinear function. This is something very easy to do. But I mean, as I mentioned, the class time in my class is so precious for me to do, algebra. But you guys will have a lot of time after you go back to your room. So I'll leave it as a practice set also, but kind of work out and see what is the exact nonlinear relation you get. But in the class, I will just try to give you some feel as to how the nonlinear characteristic will look like. That's all. So let's say I directly try to sketch qualitatively the nonlinear characteristic between the differential current and the differential input voltage. So first tell me, if the differential input voltage is 0, what can you say about the differential output current? 0, that much is clear. So this is going to start at 0. Now for very small changes in V1 minus V2, what can you say about I1 minus I2? It's going to linearly increase, and what will be the slope of this line? GM. This is the GM of the differential pair. Right? Again, we are still in the small signal regime. I'm assuming very, very small input, so it's linear. So let us say now I keep increasing V1 minus V2. That is, V1 is increasing, V2 is decreasing. If I keep doing this, after some point, what will happen? All of I0 will flow through I1. So which means the differential current will saturate to I0. And at what voltage this complete steering of current happens? Huh? Yeah, I mean, I don't want any unknowns, right? V2 also I don't know. Someone was saying something. Root 2 times the overdrive voltage. Please remember, we calculated when we looked at slew rate. There also same thing was happening. So this voltage is roughly square root 2 times the overdrive at I0 by 2. Yeah, what you told is correct, but finally I don't want any unknowns, right? So if I sketch it, basically after some point it will do this. Maybe I'll draw it slightly more realistically. In the negative side also same thing will happen. It will saturate to minus I0 at the same differential input. So let's make some observations on this characteristic. Firstly, tell me if this characteristic is odd symmetric or even symmetric. Odd symmetric. Does it make sense that this characteristic is odd symmetric? Why so? Yeah, why? Yeah, I mean that is same way of saying that it is odd symmetric. Why is it? Why? I mean, why can't it be even symmetric? Yeah, I mean that is all. Let us say you don't even know how the circuit works. Can you like convince me that this? Sorry. Yeah, I mean, as we just saw, if you have a fully differential system, what can you say about the nonlinearity? All even terms get cancelled, only odd terms will remain. So same thing is happening here. This is also fully differential. So which means I'll not have any even order terms. I'll have only odd order terms. So the characteristics will be odd. So which means I can write my differential current delta I as some GM1 times delta V plus GM3 times delta V cube plus other odd harmonics. Is that fine? Now second observation you can make is this. This is what we call as a compressive nonlinearity. And why am I calling it compressive? I mean, see, as I increase the input voltage, the characteristic sort of compresses, because in practice I can also have an expansive nonlinearity like this. That is, as I keep increasing the voltage, the current can sort of expand. And the simplest example for that will be your simple MOSFET. Here if I apply the voltage and measure the current, you know the characteristic is actually expansive. Correct? Is that correct? But here in a differential pair like this, the characteristic is actually compressive. Yeah, I mean what I'm saying is, in circuits you don't always expect that the characteristic is compressive. You can also have expansive nonlinearity. Yeah, why that is happening? Yeah, that's because you have constrained with a tail current. That's true. So now a question to you: if you know that this characteristic is actually compressive and it has only odd order terms like this, can you make any comments about the product of GM1 and GM3. In particular, do you think it is greater than 0, less than 0, or equal to 0? Why? Why? Again, it's a math question. I give a nonlinear function f of x. I know that the f of x has only odd powers of x, and the function is compressive like this. So then, yeah, why someone told it's less than 0?
The terms cancel out.
Can you explain?
When we have delta x to be, if all the terms are positive,
right,
we have delta x, delta v to be very high, then
exactly.
the terms will add up.
Yeah. So
around solution.
exactly correct. So to elaborate on his point, let's say I start with very small values of delta v. Among all these terms, which term will dominate? First term. So if I keep increasing delta v, what should happen to the current? For very small values of delta v, this is the approximation. So if I increase delta v, current should increase, and that happens. Now if I keep increasing delta v further, now which term will start to dominate now? Or which term will start to come into picture? Now we will have to consider both terms. Now I know that if I keep increasing delta v, current increasing further or reducing? Reducing. So which means this term should be positive or negative. That's all. So this is actually less than 0. Similarly, can you tell me what might be GM3 times GM5? Do you think that will be greater than 0 or less than 0? Why greater than 0? Okay, so if you are saying this is greater than 0, if GM1 is positive, GM3 is negative. This is negative, this should also be negative. So which means if I keep increasing delta v, this should actually come down, right? So what should happen now? GM5 should be opposite, right? So you'll always have that alternating behavior. I mean, all your Taylor series expansion you would have learned, right? Some of them will have, odd terms to be negative, even terms to be positive. All of them will exhibit some sort of behavior like this. Without going into maths, by logic you can actually argue. Sorry, this is actually less than 0. Everything is less than 0. Okay?
So in that equation, are we considering delta v as the complete signal or just a small signal?
No, it is a complete signal. V1 minus V2 I have defined as delta V. Okay, if that is not clear.
Why did we consider GM1 to be the constant? Isn't it beta?
No, hold on, let me mark it here. I didn't understand the question.
Delta E is equal to GM1 delta V plus GM3. If we are considering the complete signal, so the proportionality factors for delta V and delta V2 should be beta, right? Like in the above equation. Like V1 minus V2.
No, I mean, you.
Exactly take GM1 if it is not this.
No, this is not the, that's what you for. I mean, I have written it as some proportionality constant. Okay, I have denoted it as GM1, GM3. That's why you work out. You take the difference between the two and expand it and find out what is GM1 and GM3. That is your job. Yeah, I mean, your question is, will it be equal to the small signal GM? That is a question to you back. And do you think by plain logic, do you think it will be equal to small signal GM or should not be? Okay, you can check. But I have just, I mean, the only thing I have written is delta E contains odd powers of delta V. That's all. The constant I have just named it as GM1, GM3 to be dimensionally consistent. Okay, cool. Any questions till now? It's clear? Cool. So now, at least now we have some understanding of the kind of nonlinearity we might expect. So instead of again going and computing the exact nonlinearity, we will live with the fact that the circuit is nonlinear. So we'll try to do something to make the circuit more linear. Because sometimes some problems are not worth like solving in detail. We just live with the fact that the problem exists and see how the problem can be solved instead of trying to see what is the root cause of it, what can I do to blah blah blah. So now we know I have nonlinearity. Let's see how we can make the circuits more linear. And let's start with this function that I have a voltage, I want to convert it into a current in a linear fashion. So I have a voltage, I want to convert that voltage into a current, and I want this relation to be as linear as possible. If I say that my current and voltage are linearly related, what is the first thing that comes to your mind? Resistor. So in principle, if you take a resistor with a resistance R, you feed in a voltage V, the current will be V by R, there is no nonlinearity, right? But of course, I mean, you can't feed in your small signal Vi here because this will have its own source resistance, the R will load your circuit, blah blah blah. So now let us say you don't want this resistor to load your input. What can you do? Yeah, so let us say I have Vi, I don't want it to connect it directly because it is going to load it. I can put a buffer. And what is the simplest way to make a voltage buffer? Common drain. So I'll apply the input at the gate, take the output from where? Drain or source? So this is sort of buffered. I mean, let me not write as Vi. So here I can directly connect the resistor technically. So let us say to start with, let's assume ideal GM is infinity. If GM is infinity, what can you say about the source voltage here? Why? Okay, that's correct. I mean, but if you don't know that expression, can you argue otherwise? GM? Yeah, I mean, assuming that the circuit is all nice and stable, we'll assume that all quantities are finite. We'll see in the next class why can we make the assumption. But if you assume all the currents are finite, the current is GM times VGS. GM is infinity. VGS should be 0 for the currents to be finite. So, is that clear? So, which means now the current flowing here is exactly Vi by R. Now, of course, now we can take the current from here, pass it through the load you want, and get the required amplification. Okay. So now, of course, this is assuming infinite GM, but if the GM is not infinity, let's quickly see what will happen. I'm sure you guys know this, but let's. Okay, we'll draw it here. So now let us say the GM is not infinity. Then what can you say about this voltage? Yeah, GM times R by 1 plus GM R times Vi. If GMR is much greater than 1, how can you approximate as? Again Vi. So we are okay. And the important thing to note here is, now this GM can be nonlinear, that is now GM can be GM of VA. So even if that is the case, the voltage you get there will be GM of VI times R by 1 plus GM of VI times R. Right? Now even if the GM has dependence on the input, as long as you make sure that this term GM times R is much greater than 1, you can still approximate this to be VI. That's the beauty about this. Right? Now I don't care what is the kind of nonlinearity in my GM, because I don't even compute now. I live with the fact that the GM is nonlinear, but I am trying to come up with ways to make my overall circuit linear. And that is fine as long as you make sure the product is much greater than 1. Right? Does it make sense? So now this is essentially a single-ended picture. Let's try to make a a differential amp. So which means earlier I was converting the voltage to a current using a single transistor like this. Now instead of that I should have a resistor at the source. So let me draw that. One straightforward implementation will look like this. You apply 1/2 of the input there, other half of the input here, and have the tail current source. Let's call this R and R. I mean, instead of having a normal transistor, in my in my old arrangement, the voltage to current conversion was done by GM of this transistor. Now that is replaced by this structure. Okay. So here, what is the short circuit GM now? Okay, what was the relation between the current and voltage here in this circuit? How is the current and VI by the current? What is the proportionality constant? GM. R, or can you, it's like 1 by R. Fine. So the short circuit GM will be 1 by R, right? Same thing. Again, you can take a fully differential case, assume that this is ground, blah blah blah, you can. So this works actually, and you can do this, but this has one problem. Let me mark it here. Having problems is nice, because only then as engineers you all have jobs. And the simplest problem is this: the moment you have a resistor here, the resistor is going to have a voltage drop across it, so it is going to eat up your swing limit, right? If your supply is very small, you might not be able to accommodate a voltage drop across the resistor. So let's see what you can do to overcome this. And for that, tell me if you want the resistor to be present for the DC picture or only for the AC picture. Only for small signals which you want to amplify, you want the resistor to be present. You don't want the resistor to be present for DC, operating point picture, right? So which means, with respect to the operating point, I don't want to connect the resistor here like this directly, right? I don't want the resistor to be providing a DC path. The resistor should come from the source, the resistor should be connected from source to a small signal ground for small signal behavior. So how can I connect the resistor to the source now? No, okay, let's not complicate things. I mean, what I'm saying is I have a resistor. Now I don't want to connect the resistor directly here, because then you'll have a DC path. I don't want to have a DC path. Only for small signal changes I want this path to be shorted. You put a large capacitor in principle. Fine. So let me draw it. So what this means is I have and this connected to small signal ground. Now but I want to make sure that the transistor DC current is equal to I0, or I0 by 2, right? So how can I enforce that the current in the transistor is I0 by 2 now? I'll put a current source. Okay. Make sense? Now of course this is only one half. I'll draw the other half also. Same thing there also. I'll have another current source I0 by 2. I'll have the same thing like right. Let me see if I can go to next page. And please remember this side of the resistor should be connected to a small signal ground. Now you don't actually have to connect it to a ground, because let us say I apply small signals plus Vi and minus Vi here. For small signals, if I apply differential mode signal, what can you say about the nodes along the line of symmetry? They'll already be 0. So actually you don't have to go and connect them to small signal ground. Even if you directly connect them like this, you're okay. Because the fact that you're applying a fully differential signal will enforce this common node to be at small signal ground. That sort of simplifies the circuit further. Now it turns out you can simplify this even further. So tell me, what was the purpose of having the capacitor here? Why did you add the capacitor? Yeah, we don't want the DC current to flow here. Fine. Now tell me, if I apply bias voltage VB here plus VB, what can you say about these two voltages, bias voltage? They will be same. If the two voltages are same, even if I go and connect a resistor directly across this, do you think there will be a DC current flowing? No. So which means, do you think the capacitor is needed now? Not needed, right? So you can actually remove the cap and actually directly go and connect it like this. So now you see that for DC operating point picture, the bias voltages at the sources of both transistors are equal, which means even if you put a resistor here, DC current doesn't flow. But for small signals, if you apply differential mode signal, this will be small signal ground. You have what you want. No, can you? Okay, forgot what. No, CMFB variant one. Okay, you are there. We were actually sensing the common mode by using two resistors. I mean, it's not same. I can understand. You can see some similarity, but CMFB is completely different, right? Is this clear till this point? Oh, tell me, why did we add the capacitor? Why did you think we had the capacitor? I mean, remember, the problem I had in this simpler circuit was the resistor was drawing a DC current. So I was dropping a voltage across the resistor that limits the maximum input outputs I can have. So I want to have a situation wherein the resistor is connected only for small signal picture, but I don't want DC current to flow through the resistor. I want to block the DC current, added the cap. Now I see that when I do this connection, I don't need to have this. Now can you tell me if we can simplify this further? That R and R becomes 2R. So even 6 years back after your 12th standard, you could have done this simplification. Two resistors in series. So you replace it with a single resistor 2 times. So this is a better, I mean I will not say better, a modified or revised version of the old circuit.
So the value of R depends on the GM of the transistors.
Kind of, and also, I mean, you want to have, now remember your small signal gain is GM times R out. Now, you first fix your R based on the required short circuit GM. Once R is fixed, you make sure the GM of the transistor is designed so that GM times R is much greater than 1. So this is looking good, but again, anytime you find that something is good, always see what is the catch, because nothing comes for free. So if someone gives a free chocolate, don't take it, right? So let's see what can be a problem, and for the interest of time, I'll directly say. So let us say now you look at the left side circuit. If this current source injects a noise current, which it will, what can you say about the noise current getting split in the two sides? They will be identical because both halves are symmetrical. So if I take the output difference, what can you say? That should get cancelled, right? I mean, this is something we saw in a fully differential circuit. Any common mode disturbance sort of gets rejected. So this adds no noise. So I will say no noise from current source. Now let's look at what happens in this case. So let us say this current source is injecting some noise current IN1. Now this current sees an impedance looking up and impedance looking to the right. Are both the impedances equal? No, which means the noise current that gets injected on the left side of the circuit and the right side of the circuit, they will be different. So now even if I look at the differential output, that doesn't get cancelled. Is this clear?
Noise current source only to the one particular noise, not by two from other.
Yeah, same. That will also, so same, it's not same noise. I mean, again, remember that if you have two resistors or two current sources of the same value, the noise power spectral density is equal, but the noise is completely uncorrelated. Right? I mean, again, you can have two batsmen having the same batting average, doesn't mean the batsmen are equal. Right? A property of the signal is equal, but doesn't mean the signals themselves are equal. Right? How are you planning to merge it? Yeah, but if you do this, then the resistor is not in. This is sort of shorted, right? Maybe you can think of some different variant, but yeah, it's not straight. So that is a disadvantage. So even this noise current, I mean this current source that will be injecting noise, that will also not get cancelled. So that is a downside to this technique, that you will have additional current due to noise sources. Still, right, doesn't matter. Even if you had the capacitor, the same thing, right? For small signal, the capacitor is shorted, right? Noise is small signal. Okay, this is one common trick that is often done. Either you do this or do this, and again each has its own pro and con. So depending on the situation, you sort of use it. And before we wrap up, remember this entire thing was based on the observation here we made. Here, not here. Here, yeah. Here the observation made was, if I have a resistor connected to the source, and by the way, this has a jargon. Anytime you come up with something new, you give it a name, and this is called as source degeneration. Maybe you have heard this in different contexts, but yeah. Yeah, and this entire principle we saw is based on this observation, that if I have something here, so the voltage I have here is Gm times R by 1 plus Gm times R. Thanks. Now tell me, have you encountered some other situation in general wherein my output is input times a quantity by 1 plus some quantity? Output is input times something, negative feedback, and in fact here there is a negative feedback happening. Okay? Because if I don't have the resistor and just have a MOS transistor, and I try to convert the voltage to a current using only a MOS transistor, if let us say I increase the gate voltage, what can you say about the drain current? That's it, it's open loop, right? Now here let us say I increase the gate voltage. Initially what will happen to the drain current? It will try to increase, obviously, because you are increasing the gate voltage. But then what will happen to the source voltage? That will also tend to increase. Now what will happen to the drain current now? So there is a beautiful negative feedback happening here, and that is what is sort of setting the current or this voltage to be approximately V. So once you recognize this, now we can actually understand that there is nothing so great about source degeneration. The actual person sitting behind and helping us get this linearity is what? Negative feedback. Right? Source degeneration turns out to be one way to implement the negative feedback. So you can use negative feedback to your advantage to improve the linearity, and we'll discuss in detail in the next class.